Let me begin from the beginning. First of all, I would like to thank the organizer for inviting me to give a talk here. Unfortunately, I was unable to come in person, so I'm talking sort of in effigy. Here is the topic of my talk. The title I don't know. Suppose we have a bounded domain M in Rn, and consider the group of diffeomorphisms which is regarded in different topologies, say in diffeomorphism of Sobolev class HS, preserving volume of M. So this group, it is a group, and it is a subset of the space of HS maps from M to Rn. No, simply because M is a subset of Rn, so any diffeomorphism of M self map of M can be regarded as a map from M to Rn. So it is some set in Rn, and to some degree all our studies of geometry of this set are reduced to the question, after all, how does it look? So we study different properties of this set. And we have to consider two different cases. First, if S is large enough, say more than n over 2 plus 1, maybe instead of 1 you have to write some other constant, more than 1 to be sure. It is one important thing, it is better studied. And second, when S equals 0, L2, so it's the energy space. So I wanted to tell you about some properties, some geometrical properties which can somehow justify the claim that I'm talking about how this set is, how does it look. So we start from the first part. S is large enough. Yeah. No, first of all, D in HS of M Rn is a smooth manifold. No, it is well-known property, so let me start. But we'll see that this smooth manifold, among other smooth manifolds inside the Hilbert space, has some rather rigid geometrical structure, which I am going to describe. So let me start without delay to talk what I'm going to define. So I consider the following first, the following general notion. Consider a map from X to Y, where X, Y are Hilbert space. X is compactly and densely embedded in space X1. Y is compactly and densely embedded into Y1. Consider the map F or better to write it capital F. Uh, so F is uh, continued can be continued to a continuous map from x1 to y1. Yes, and it has the following structure: f of u equals g u of u, where for any u in x, for any u in x1, G U is a affine space, affine map, I mean linear, non-homogeneous maybe with some shift between x and y. G U depends continuously on u in x1. So it is such map F is called quasi-linear. Quasi-linear map. So now I have a claim. Claim, this means that it is not a theorem, it is sort of general principle. Claim. Any reasonable nonlinear operator is quasi-linear. Any reasonable, what I call reasonable, it is not well defined, but I will give you some examples and then you will see what I mean. So let us start from from a simple example. Let x and y equal hs on the segment from 0 to 1. It's enough. And x1 is y1 equals hs minus 1 from 0 to 1. And suppose we have the following operator: fu of x equals some function f of u of x, just operator of composition, where f is a smooth function, arbitrary smooth function. So I claim that this operator, this superposition operator, is quasi-linear. In fact, fu of x equals f of u of x equals, let us do the following, differentiate and integrate it. It is f of u of 0 plus integral from 0 to x f prime of u of s u prime of s ds equals gu of u, where gu of v equals f of u of 0 integral from 0 to x f prime of u of s v prime of s ds. Yes, and just look, if u is an hs, if u in h s minus 1, then gu from hs to hs continuous affine operator. Why? Because this, if v is an hs, then this is in hs minus 1. If u in is hs minus 1, then this is also f prime of u in hs minus 1. No, I use theorems of composition of Sobolev function and smooth functions. Next, if you have two Sobolev function is hs minus 1, then their product is also in hs minus 1, because for sufficiently large s, the space hs minus 1 is an algebra. So all this in hs minus 1, and now we integrate it and return to the space hs. Yeah, and so this operator gu as operator from h to hs to hs depends continuously on this parameter u in space hs minus 1. Now, if you think a little more, you will see that gu is para differential operator from hs to hs is symbol f prime of u of x, yeah, where u in hs minus 1. This is the simplest example of such operator with reasonable symbol. So we say it is operator acting in the space of smooth function. Its symbol has less smoothness, and nonetheless it works very well, continuous. And this is possibly the simplest, the first instance of part differential operators, which gave later rise to more involved examples of part differential operators. Now, if you have a linear operator and this quasi-linear operator, then the composition is also quasi-linear in both orders. Yes, if you have two quasi-linear operators, then their composition is also quasi-linear operator. It is all proved straightforward. Yes, if you have a quasi-linear operator such that this operator bu or gu for every u is linear and invertible, no, say there should be elliptic quasi-elliptic GU, elliptic part differential operator. Then the inverse of such operator is also quasi-linear operator. And so any composition of operators of a composition with nonlinear smooth functions and linear operators, say differential operators, pseudo differential operators, all rational compositions are operators of the same class of quasi-linear operators. So for analysis, no, at least no, okay, for large part of analysis, we have no other operators than this, which are obtained from elementary pieces like composition with nonlinear smooth function and linear differential or pseudo differential operators. It is all operators which they work with. But the necessary condition for this paradise is that we are working in a space of sufficiently smooth functions, HS for sufficiently large S. So it doesn't work in less regular spaces. Now it is the first thing. Now I wanted to go to some geometrical property of these operators, of quasi-linear operators. And consider the notion of first of ruled operator from x to y. Operator, I interchange operators and maps. X to y. These are two Hilbert space. Now suppose that x equals union of x alpha, alpha in say R and capital. So x alpha parallel planes of codimension n. Yeah, and so these planes x alpha are somehow parameterized by point alpha in Rn. Everything is fine. And suppose, consider the map Fn from x to y, such that Fn if you consider it on the plane x alpha, is a fine map from x alpha to y, depending continuously on alpha. Yeah. So it looks the following. This is x is foliated into parallel planes x alpha. In y image of each of these x alpha is some plane, a fine plane, which depends on alpha, so but they are no more parallel, they can rotate. Now, among all these maps, I consider Fredholm. Fredholm ruled maps. Such that f and on each x alpha is Fredholm map. This means that its image is the plane in space y of the same codimension, and the inverse map from the image to x alpha is also continuous, and also depends continuously on alpha. It is the geometric picture of sort of elliptic elliptic picture, but elliptic map, but it is a ruled map. And next goes the notion of quasi-ruled maps. Map. It is the following: f from x to y, such that in every, say, ball B in x, f can be uniformly approximated by ruled maps Fn. So uniformly with arbitrary accuracy. And F is Fredholm quasi-ruled. Fredholm quasi-ruled no, if Fn are uniformly Fredholm. Yeah. Okay, uniformly Fredholm. No, in obvious sense. So I would say that claim every nonlinear, say, part differential operator defines a Fredholm quasi-ruled map. No, in between corresponding, say, Sobolev spaces. No, the examples of Fredholm quasi-ruled map are claimed here. Why it is a just claim and not a theorem? Because there is no real definition of nonlinear nonlinear paradifferential operator. We have some examples, but we have no general strict notion what is this paradifferential, what is not. So it is a little bit fuzzy concept, but it is nonetheless true. Yes, and we'll see a remarkable example of such operator in about 10 minutes. So now, what is not quasi-linear operator? So we have examples of quasi-linear operator, but which it is important to understand what is not quasi-linear operator. So example, the following operator, say f, which takes u and moves it to, say, norm u square plus 1 times u, yes, no, in x. X is, say, Sobolev space. This operator is not quasi-linear operator, though it is smooth, and even it is smooth diffeomorphism of the whole space X into itself, but it is not quasi-linear because it is not quasi-ruled. Why it is not quasi-ruled? Because it is curved in every direction. Yeah, so it is second derivative along every line is positive and does not go to 0. It's bounded from below by 2. So this operator is not quasi-ruled, so it is not quasi-linear operator. Note that in different constructions of infinite dimensional topology, we use the maps like this, and no wonder that we get empty theory. First, it is empty because it has 0 intersection with what we need for analysis, and second, it is empty because it turns out to be pathological. So now I have to define now quasi-ruled manifold. First of all, ruled manifold. Say Xi in X, yes, it is Xi is union Xi alpha, alpha in Rn. Yes, Xi is union of Xi alpha. Xi alpha plane in X. No, fine. Plane in X. No, continuously depending on alpha. So it is like ruled surface. In ruled surface it is just line, and here it is plane in X. No, in general it has uh, infinite dimension and infinite codimension. Quasi-ruled manifold. Xi, let me call it Xn. Xi, no, N here. Xi can be approximated by ruled manifolds in any, say, ball B. Yeah. No, in what sense approximated? I think it can be approximated not in the C, but also in CK for all K. I think this strong claim. And now the next claim is that if F from X to Y is a quasi-linear operator, then F minus 1 of some, of say 0, no, okay, Y0, Y0 in Y, equals, say, Z is a quasi-ruled manifold in X. Yeah, so we have a quasi-ruled manifold. Now we can consider now example of our group D in X, which is HS from M to Rn, small. D is described is defined by the following conditions. First, the boundary of M should go to M. Yes, it is one condition. Now the boundary of domain can be defined by some function, and so we have a condition that we have to define f of the image of our of any point on the boundary should be on the boundary. It is the function of the image of this point should be, again be 0, so it is one component, and other component that the Jacobian of this map which we consider the map f, not f, let me call u, from M to Rn, Jacobian du dx should be 1. It is another condition. Yeah, Jacobian is the map from HS to HS minus 1, and it is also a quasi-linear map in our sense. So we have exactly in the setup of this theorem. So the group D is a quasi-ruled manifold, smooth quasi-ruled manifold in the space HS, yeah, from M to Rn. And now we consider the maps between quasi-linear manifold or quasi-ruled manifold. And let me go um, further. I should so we can define what is the quasi-ruled map between quasi-ruled manifold. First thing, it is a limit of ruled maps between ruled manifolds. And then we consider the following map. Geodesic exponential map from T D at the identity, yes, it is vector field, to D. And it is time 1 exponential map. So we push the liquid, the fluid in the direction of vector field U, and we see what is diffeomorphism after time 1. And the theory, it is the theorem. This map is first Fridholm quasi-linear and Fridholm quasi-ruled. And second, this map is an elliptic paradifferential operator of order 0. No, in fact, we have to change places between 1 and 2, because first we establish that it is elliptic paradifferential operator, and even we have, I can write almost exact, almost explicit formula for this map. It is the first part, and then as a consequence is that it is going quasi-linear and quasi-ruled. And 3, it is positive definite in some sense. Unfortunately, the proof of these things required a little hard analysis, and I have no time now to go in details about this. So it is the most important for us example of all this construction. First, we have quasi-linear and quasi-ruled manifold in the Hilbert space, and second, we have the the map from the linear space to this manifold, which is also quasi-linear and quasi-ruled, and even has positive definite, means that we have some good a priori estimate. Now, if you did not understand what I am hinting at, it is the following scandalous situation. We know that if you have two-dimensional domain, then if you have initial sufficiently regular velocity field, then solution exists, and it defines continuous flow uh, in this domain. And the question is, can we push the fluid along some vector field so that after time 1 the fluid assumes a given configuration. So every fluid particles comes to its prescribed position. Yes, or in other words, does the exponential map, the image of exponential map, cover the whole group D, the whole manifold D? Um, uh, I say that it is a scandal that this is not proved still now, and we have some local results. Say it covers some neighborhood of unity, but the global result like this is not proved, and this theorem, all this theory, is a way to use here classical very classical topological methods like Leray-Schauder. No, it is some extension of Leray-Schauder to prove this theorem. No, to establish this covering property. Yes, I. There is still no theorem. There is hypothesis that it is covering. Yeah. So this is the I would say supreme goal of all this theory. So this is what I wanted to tell today about the first case when we consider our group of volume preserving diffeomorphisms as a subset of the Hilbert space. Uh, okay. No, okay. Now consider other case, even more interesting, when we consider that D is as a subset of A2. No, first of all, D is not a smooth manifold, not a manifold at all. This is quite important. Now, to explain why it is true, consider the following thing. If you have, say, F and G in D, we can consider two distances. The first distance is simply distance between F minus G in the space S in A2. It is the first distance. And second distance is the following. We consider all ft, t between 0 and 1, and such that f0 equals f, f1 equals g, and consider the L of ft from 0 to 1, integral from 0 to 1 square root ft dot let me write this way. Norma ft dot in x dt. It is just the length of this curve, and d between fg equals infinitum L ft among all ft, connecting f0, f and g, the distance. So what can we say? First, if n equal 2 in two-dimensional case, d is not uh, uh, connected set in the metric d. This means that for any f, for any epsilon and any f in d, there exists g in d such that norm f minus g less than epsilon and d fg is infinite. They cannot be connected by a finite by a path of finite length. So it is totally disconnected. Now the set of components connectivity is continuum. So it is completely out of joint. If n is more or equal than 2, more or equal than 3, then this is not true. In this case, the diameter of d, no, in the sense supremum of distances, d distances between different points is finite, first of all, and moreover, we have the following estimate d of fg less than c norm c n f minus g in x to some power alpha n. Yes, this, no, for example, in 3D, alpha 3 is more or equal than 2/7. Yeah. So this no. Here we need opposite estimate that some lower estimate. So it is upper estimate. We need some lower estimate of distance. So this means that we need some beta n such that d f k gk, I would say, for any is less than norm more or equal fk minus gk to the power beta k. Yes, so for any there is some beta n. So there exists some beta n which is beta n less than 1. Such that for any epsilon there is fk and gk, and the distance between them is more than this distance along the straight segment to some power b beta n. No, it is still not done, while I have feeling that this beta n should be also close to this in 3D. But I would be happy to have any beta n. So all this means that this set is not a smooth manifold. By the way, here f can be arbitrary constant map, and G is exists for at any small distance in the sense of the norm. There exists G k such that f minus gk for we have this inequality. No other things which can be said about it. Other statements is that we have internal map D, and we can consider D. It is completion of D with respect to the distance D. Yes, and D bar closure of D in X equals L2 M Rn. And the theorem is that the completion is no, in natural sense, identical to the closure. No, this means that we can reach any point of D or even D closure of D going along D this set D, and we reach it in by the way of finite length. However, my last statement is the following, statement of intention. We have the following situation. In the L2 is a really physical meaning space. So our liquid is, after all, a collection of continuum of particles with some constraints. Constraints are given by the set D. And we are moving along the set D, and we have to describe this motion. How can we do it? If the D were smooth manifold, we could use same machinery of D'Alembert principle and write the equation, which is exactly the Euler equation. Yes, so Euler equations are derived in assumption that this manifold D is smooth manifold. But if D is not a smooth manifold, then we have to start all this work anew. We cannot use this notion of the normal vectors and so on, because we have no normal vector, no tangent planes, at least no tangent planes in the usual sense. And so we have a general problem how to describe the motion along the rough set, which is not a surface, not a manifold, some rough set, just locally connected, but very tricky. which is interesting even in finite dimensional case. Consider a rough surface, say, and we are moving along this, a particle is moving along this surface. How to describe its motion? What is the sort equation or some other? I don't think that it is described by some sort of equation. Um, so it is a real domain of speculations. We have to construct it. And what I have to say about this should be in other talk, which possibly I will give some other time, because it also requires some work. We can define it in some sensible way, but it is not straightforward. And it has the direct relation to turbulence. So but I won't start a new talk in the last minute of this talk. So let us take it as an announce of the next talk. For now, let me finish. Thank you very much, and if you ask me questions, I will be happy. Thank you. Bye.